to acknowledge hard work that all of you have done by now. We should realize that it is not a regular procedure. You sacrificed your time and invested, I think, more than typically into this course, and it should be a really great initiative to make these presentations. So the goal of the meeting that we are doing right now is to share the practical skills to operate VASP software, DFT software, because we want to add a practical component to the lectures. So we spend additional time in the lab, which is not recorded, not broadcasted as a part of the lecture, and in case some of us was not in one or another meeting, we want to come to the same page for the whole community of the class and follow what is going on. So those practical skills that we are going to share today are of vital importance for the independent research project that we will be doing as the final chord of the class. And I'll get back to this slide in a minute. Let me announce the plan for rest of the course. So we are finishing everything by the end of April, and we have total 6 lectures left and 3 meetings in the lab. So the last meeting, it would be great if we have our independent research projects done by this time, and we do our last session of presentations, presenting whatever we found. So it is, well, now let's concentrate on practical skills, but right after we finish this meeting, it is time to start thinking about your independent research project. So you're completely free to choose whatever looks attractive, whatever can be beneficial for your major thesis research or what you have curiosity for. But just in case, I made several suggestions last time, and here I finalized them in a more detailed way. So it is not a prescription, it is not a requirement, it is just a suggestion. You can choose whatever you like. So I just write suggestion near each name, and please email me back during this weekend, and we'll discuss how you create your simulation cell, or maybe I will help you to do it, and so that you spend the rest of the time productively. Because in my opinion, this is major part of the course. Okay. So another announcement that I need to be on the conference next 2 lectures, and there will be a replacement lecturer. Dr. Huang is in the audience today, but we discussed and agreed in details, so it will be a regular continuation of the course. It will be not something aside, apart. It will continue the same general line, bringing all of us to research projects, the success. And I will, while I'm not in the city, I will leave keys with one of you, so that if you like, you can gather in the Arts and Science basement and do your projects. Okay, so by now we did complete 2 oral sessions, one of the building atomic models, another on utilizing Gaussian software, and today we want to complement our density functional theory studies by the practical skills, how to run DFT calculations from the practical side. So we are going through all ladder steps that bring us from setting up actual calculation, from inserting the geometry positions of ions, towards finding several characteristics of the materials. And there are total 7 presentations. We can try to spend 6 minutes for each of them. So if it takes longer, then I will be watching time. If it takes longer than 6, I will just start making signs that it is about time to stop. And then we should go ahead and ask questions to the speaker, because a person who was focusing on each specific subject may become an expert in this field, and the rest of the audience may learn something helpful. So subjects approximately follow what we were doing in the lab. So preparing input, analyzing output, modifying electronic configuration, necessity of spin polarized DFT, absorption spectra, thermalization of models, and then most visually appealing part, how to consolidate the data in form of movies. So for presenting, you are invited to come up front to this stage, to the desktop, and navigate to one of your presentations. So all presentations are arranged according to their order in our schedule. So first one, second one, third one. Then it is also duplicated with the name of presenter, so it shouldn't be a big difficulty to navigate. So you're opening the first one, or whatever. Then navigating to this symbol of presentation, just in case. I'm sure you all know this. Click here and start presenting. And if you want to answer questions or make some marks, you know, this technology allows to write something. Just, some concepts could be difficult to explain by words, and you may want to draw something. Okay, with I will also distribute the handouts, consolidating everything you need. So with this, I'm inviting first presenter Mohammad to give an introduction to how to run VASP jobs and what is necessary to do this. You can hold it or mount on your ear.
This work. SDSU, are you hearing me?
Yes. We can.
Actually, I will give you overview of DFT and how we can prepare input files for VASP software. First of all, it's DFT theory. We're going to talk about total molecular Hamilton. As we see here, we have Hamiltonian has potential of electron, and electron nuclear, and nuclear atom. Also, we should consider Oppenheimer approximation, which has given us possibility to handle large molecule being point of departure of the computations. From the view of electron, Fock operator give you also a combination between column operator and exchange operator. Hartree-Fock-Rotten equation give us Fock matrix and times vector coefficient, also provide energy of matrix and overlap matrix. Solution of this equation yields the Hartree-Fock wave function and energy of the system. Density functional theory, it actually deals, we talk about density. So density instead of Hamiltonian or wave function, mapping space vector to scalar. Cohen-Sham equation give us total energy, how in terms of Coulomb kinetic energy and external potential Coulomb energy exchange correlation energy. Um, right now, what we need to prepare files for VASP. We need in-car file which contain all the control parameters that determine what to do and how to do it, and can contain a relatively large number of parameters. Most of these parameters have convenient defaults, and a user unaware of their meaning should not change any of these default value. Key points files also contain the key point sampling scheme, all the information with regard to your key point set accuracy increase with number of key points. Both contains information in unit and the basis atoms. Both card pseudo potential file used by VASP contains all necessary information related to the treated chemical space, then wave basis set, atomic radius, atomic mass, total, and valence electron number. So I borrow this scheme from Dr. Kalen PowerPoint. So it shows actually we study this system, how we can choose a piece of the whole wire and measure. As we see here, we have chosen some of unit replication, and in the software we can measure the distance between A and B atom, as we see here. So we can see the X, Y, Z um, directions, and then we can measure the difference between the X direction here. The other step is just as we learn, uh, go to create new folder, transfer this folder to previous folder as we see here. Should be in XYZ direction, XYZ extension, and we see here the adjustment in angstrom to avoid spirals interaction with periodic replicas. The distance is like the adjustment 1.35 in this system. We need also to form the Boscar file, so we can form this by this here. You notice how we can start initiating Boscar file, and we can also modify Boscar file by make sure first line has number of ions, second is empty, the third start coordinate for each atom. Then we notice how we can form Boscar dx, dy, dz file by use this command here. So these commands actually define the periodic lattice vectors and give us at the same time here like rotated coordinate in tank format source, and also the numbers down lattice correction along x, y, and z in angstrom. See here the publication again. We just go back until this one. Once we form x, y, z, rotate x, y, z, until this step, this command cannot run VASP. You should also form another command. You should have both car files, and you can just run this command, form both car file, and also is in oxygen because we have titanium and oxygen. We have also on titanium, and then form another one, which most important one also is NCAR file for geometry optimization and key point file. Once you have right now all these files, you can run VASP, because we already mentioned we should have 4 files to run VASP. Right now, if you will look this in NCAR file, actually you can choose this most important things. NCAR has more than one type file in car. So if you need geometrical optimization, you choose one file template. If you need to compute orbital, also you choose from the template here. It has more than template. You can choose whatever the mission you want, either geometry optimization, orbital compute, whatever, and this from NCAR. This one, it's actually about the compute orbitals. It has more than you can get more than one information, like the first line, type the job, evaluate partial decomposed charge density, and also uh, like this one, symmetry is not considered in calculation. It's also number of ionic steps, time step. All these information you can find in NCAR file. We have also example of key point file. If you run more key point, you find something like this screen. It's give you this number 32 is this example discrete momenta in z directions, and the periodicity and distribution of momenta must match the same directions. This also another example of NCAR for geometrical optimization. Use it as I mentioned, use it for the template, and you can, if you want geometrical optimization, you can choose this file and get the mission you want. And I would say thank you for your listening. I'm here to answer your question.
Excuse me,
Yeah,
Mohammad.
thank you, Mohammed. Let's thank the speaker.
Can you hear me?
Go ahead.
What are the things we can change in in-car? There are lots of things, so what are the specific thing that we need? Or
Okay, so it's actually in car you have template. So if you want geometry optimization, you can go to one of the files and choose it. You know, if you want draw orbital, you can choose another file.
there are different key in-car files for
Yeah,
different
it's
things.
actually for each mission there is I would say template, special
Oh.
template.
Okay. What about key points? Can you briefly tell a little bit more key points? Yeah.
Key
How we
points,
make-
it's regarding actually the if you notice if you're gonna draw or animation you want, you should has number of key points in your file, and I would say no much you can change in key point, but the number distribution of momenta must match the directions. Like here 32 is discrete momenta in z directions, must match the direction you have or the momentum you have.
Okay. Thank you.
Any other questions? Okay, let's thank Mohammed once again. The next speaker is Qiang, and it took 10 minutes for presentation plus questions, so let's try to have a primary goal 6 minutes, and 7 minutes and 10 minutes will be hard limit. So then we will finish in 1 hour and 10 minutes, and we shouldn't go for a longer time.
Hello everyone. Today I'm gonna talk about two parts. First the outcome file, and then the Chem orbitals. So there are a lot of information we can get from the outcome file. First we can type this command, and then we can have, as what I showed in here, the orbitals and their energy, and also the occupations. And after that, we can also see the states by typing this command. So in order to write the DOS file, we have to know certain informations, including here the number of electrons and the Fermi energy alpha bit value. So we can get this information by these two commands. And then there will be like a bunch of questions asked about the values we got previously, and when we trying to draw this DOS file, and then after answering all those questions, we can plot the DOS file here, and then save this in the local computer for the PDF file, and then it shows the figure like what I'm showing here. The other thing is so in order we want to plot the different orbitals in the VASP wheel. So in order to do that, we have to create the parch file, which the template is provided in here. So we have to adjust the in-car. And then here, this figure, we can see after that done, we can see we have all the file created in the folder, including the charge car, and also different orbitals, which is shown in here. So for the charge file, here is the total charge density, and on the right side we can see they have a yaw, pitch, and roll. If you try to change the number, you can see the whole structure here is actually rotating or just going different shape and moving. And here, this one is a charge car file. One thing I have to mention in here is when you first open this file, actually you didn't see all these orbitals. You just see the atoms like in blue or red color. So in order to have that, I'll mention that later, sorry. So we all notice on the right side they have an operation system which have 5 functional panels, including the data, atoms, bonds, views, and options. So in this data one, we can adjust the ISO surface value, which is what I just mentioned here. When you first get it, you only have these atoms. So by adjusting those value, you can have the atmosphere around it. And then as atom one, we can choose the different atom radius, so we can get like larger model. And the view, like I just mentioned, is have 3 different orientations. You can adjust the shape and the way how it rolls or something. So at the very end, you basically just seeing this figure's background color. If you want it to be easier to observe this here, you can choose it into the white color because when you first open the file, it's normally black background. So the ISO value we chose normally, well, I tried like all my files. Basically, if you have the value below 100, you can see this orbitals. Yeah, this one is the homo orbital, which is orbital number 32. And the LUMO shows like this. No electrons.
Okay, let's thank Qiang.
Yeah, I have a question. This outcar is basically after we run VASP, we get this outcar, and then it is for plotting things.
The
in a
outcar is after you run the
VASP.
VASP, well, you got the, and then it created automatically.
Oh, okay, thank you.
Any other questions? Okay, let's thank Qiang once again. And the next speaker is Shelton, telling about how one can modify electronic configuration of the system. So here I would like to make a comment that the model of some material that we are simulating is determined primarily by positions of ions. But for given model, one can explore different electronic configurations: ground, ionized, excited, and Shelton will explain us about these things. So please.
Good afternoon, everybody. How to modify electronic configuration of the model, as Mohammad mentioned in his presentation.
Can you take that mic a little closer? Yeah.
Is it okay now?
Yeah.
As Mohammad mentioned in his presentation, we have to create a separate directory for each and every task which we are going to do. So for an example, in my case, if we are going to modify the electronic configuration for cation, then we have to create a separate directory with the name of that model followed by the cation. Or if you are going to create for anion, then you have to create the separate directory for that anion. Like that, you have to create the separate directory in order to avoid the complexity when we are run the command. So like this, here I am going to select the model which we have used in our practical session in the laboratory, that is titanium 408. So that I have created the directory. So before I going to modify the electronic configuration, I have to know that how many valence electrons are there in this model. In order to find that, I have to type grep nelect outcar and hit the enter. Then you can find that how many electrons are there. You will see that n electron equal to 64. Once you find it that, then you can move. If you are going to create suppose anion, then you have to create a separate directory as I mentioned earlier, anion. Then you have to type vi inca. Vi for just to modify, that's a command to modify the inca file. Instead of vi, we can use nano also. Then once you type it and hit enter, then you will see that this scene, you can see that. So then if you want to modify that, you have to press insert key. Then in the insert key you can see that there's a cursor. To move the cursor, you can use that arrow. By using that arrow, you can move the cursor end of the I spin 2 and hit it. Then here you can type n elect equal 65. Then now you have modified this Inca file for anion. Once you serve this work or modification into this Inca file, you have to press the escape key and write W, that is for write, that is for serve, and Q quit, and explanation mark, and hit enter. Now you have modified the Inca file for anion. So if you want to check whether it is modified, just you can type grep n electron outcar and hit enter. You can find it that now number of electrons is equal to 65. Now it is modified. The same way, in order to modify the electronic configuration for cation, I have to create the separate directory for cation and type vi inca. Now it is open. In order to edit this, move the arrow key and hit it enter and type number of electron equal to 63, and now you have modified it. So in order to serve this modification, as I mentioned earlier, press escape and type colon, then write, quit, and explanation mark. Now it is modified. So now up to now I have modified the electronic configuration for cation and anion. Now I am going to modify for excited state of the model. Now before that I have to give small explanation about what is Previa and Peredo. Previ is the set of occupancy of the states in the upspin channel. The Peredo is that one occupancy of states that's downspin channel. This occupancy must be between 0 and 1. In the same way, like which I have explained to anion and cation, we can modify this electronic configuration. In this, again, you have to copy that 4 files into the separate directory which you have created for excited. So then you have to type these 2 commands, that is insmear and other one is Previ. These 2 commands which you have to modify this in order to do that. Then now you can save it the same files, and here only I am going to show that how to create the DOS down and DOS up. Just I am going to explain only for that excited model. Okay, it will ask some questions. You have to answer for these questions, and you will run it and VASP. Run VASP, you can run it. Then here is the experiences I had when I type this the answer. Here you see prepare the file state of number of energy occupations. Here it is 46, but in the case of down, so this is one is for down, but in the case of up it is 48. So I was so struggling that when I am running this one I couldn't get it. Then Dr. Killin explained me how to find this 46. So this is depend on when we are creating the down. So things we have made some mistakes, and based on that we had find it that according to that. So then due to that, here is the problem is occurring when I am running that I couldn't get the PDF file. When I am running I can't specifically create the PS file. Based on that I can't create the PDF file. I think these shortcome you will be realized, and you will come to conclude that the coming presenters they will explain it how to do these things. So what is spin polarization? Spin polarization is the charge to which the spin, the intrinsic angular momentum of the elementary particles in aligned with give direction. So how to do this spin polarization or non-spin polarization? For these 2 calculation also we can edit these in the Inca files. So if it is IS spin is equal to, then there should be a spin polarization calculation. If it is 1, then non-spin polarization calculation that will be helpful. Yeah, what is nub down? Nub down, the difference between the number of electron in up and down spinning component, which allows the calculation for a specific spin multiplier. So the nub down can be set in the Inca file as the same way which I explain in previous electronic modifications. So like this, in the same way we can give the values. If it is nub down is equal null or -1, that is a full relaxation. So this is also the default one. If you put the 0, that is singlet. So if it's nub down is 1, that is doublet. So if the nub down is 2, then that is triplet. So this the difference between the spin polarized and non-spin polarized calculations. Self-consistent spin polarized calculation can be started. As I mentioned, the setting I spin, we can do the calculations or total energy through by using the spin polarized or non-spin polarized methods. So the accuracy of the both are same, but the which solution is more reasonable only depend on whether the system really is magnetic or not. If it is, the calculation has to be done spin polarized, and the total energy of the cell will be more negative than for the non-polarized calculation. If it is not, then magnetic momentum will be 0, and then the energy should be in the same as for the non-spin polarization. Thank you.
Yeah. Thank you very much, Sheldon. Let's thank the speaker. It was very nice to show this lines developing in time. Very instructive. So, any questions to the speaker? Okay, if there are no questions, let's thank Shelton once again, and go to the next presentation by Stephanie. So she will tell a story how to visualize the results of the spin polarized calculations and refresh our memory about what is density of state concept.
So basically our density of states just shows how many states are present per interval of energy. It can also show, like our calculations also show whether they're occupied or unoccupied, represented by fill. And a 0 implies no states exist at that energy level, so like a band gap would have a flat line at 0. Spin polarization is needed, especially when working with metals. For example, like we know the Aufbau principle for titanium and cobalt both have unpaired electrons, so we should be using spin polarization when dealing with those elements. If all electrons are paired, it's not needed. So when we use this spin polarization, it follows Hund's rule, and that basically say we want the maximum value of S. So all states are singly occupied with parallel spin before double occupation occurs. A good way to look at this is the bus seat rule. So most people will sit by themselves until all seats are full, and then people will start doubling up. So this just shows a little schematic on the different calculations we can do. For DFT, you just see they automatically pair up, and then the spin, I spin equals 2, which is what we're using now. You see the 2 separate orbitals, and then DFT spin, which is, I think, a little bit more relevant to F orbitals. You can see the splitting here between them, and you can define how many pairs of electrons you have based on your new N up-down. So we just run geometry optimization as normal, and you change, as explained before, the I spin and N up-down. And the N up-down is used if you want to intentionally violate Hund's rule, force an excited state, as it was explained earlier. And you just, yeah, we went over that already. So here would be a caption of what you would see with the adding electrons and I spin values right here. So how to extract the density of states? You need to inspect your outcar file. First, make sure it's correct. It should be about 3,000 lines with smaller molecules. So if it's really small, you probably did something wrong. So VI outcar would be the line. And then there should be 2 lists of orbitals when using spin, and only 1 for non-spin. So over on the left, we have you see that we have spin component 1, which would be our up, and spin component 2, which is our down. And in the bottom left corner, when you're looking at your outcar, it will tell you what line you're at. So note that this is 2,294. And then in order to create our states up and states down files, use CP outcar as states up, and you do the exact same thing for states down. So initially they'll be equal. And then you remove all excess. So you've visualized states up, and then you can either do DD, which will eliminate single lines, or you can do, we knew we were at 2,294, so type that number and then press DD, and it'll go directly. It'll delete all those files above, and then delete everything below. And all you should see is the list of orbitals, the energies, and the occupations. You don't need anything else. We don't need any headers or anything. And then do the exact same thing with the states down file, but make sure you use spin component 2 when creating that one. So we run the code, both dress DOS down and dress DOS up, and then the series of questions, and then this just goes into detail explaining how to answer these questions. So your number of states is in your states file, so 48, and it can be different for up and down. Your minimum energy and maximum energy, you just need to look at the range of energies you want plotted, and this will make sure you include your band gap, and then you can usually go 10 up and 10 below that. For line width, we use 0.01. This is technically theorized to be the Boltzmann constant times temp. Magnitude is 1. Your number of atoms, the number of electrons using the Grep-Nelly outcar, and then gap bulk phase we use 3. So this is just a screenshot of what it will look like when it asks these questions, and then you answer one by one. So after we implement the code, the dos.down and dos.up file is created for dress DOS down and dress DOS up. Then we plot it with the new plot command, and then we see one file is created from those two. We get dos up-down.ps. We convert it to a PDF using the ps to PDF WR command, and then we can copy that onto the computer using the SCP, and then if you just type PWD where you're working, it'll give you your pathway, and then the name of the file you want to copy, followed by a space and then a period. And then so for a cation, we see this, and the equations there are just what we use to plot these. So these would what you would find in like an academic journal. And it's basically just the Dirac delta function, which gives it its nice Gaussian shape, and then the energy differences. And so you can see the cation has one filled lower orbital, and then if we go to the neutral, we see it's completely even. And then at the anion, we have an extra electron there. And so just a summary, this was just for spin polarized. When you have the unpolarized restricted DFT, you just have one states file because you only have one set of energy levels. And then when you use the dress DOS norm, you don't have underscore up or down. You just use dress DOS normal, and everything else is the same. About it.
Thank you very much. Let's thank the speaker.
Excuse me. Can you tell me what is how you get that 2294 value as second or third? Yeah, these
Yeah.
three.
So when you're here, if you look down here, you find where these components are, the spin components, and then right here, if you get your cursor to that line, it'll tell you you're at 2294 here.
Oh, okay.
And so it tells you where you're at.
Okay.
And then what I usually do is, like, if that's the case, I go to like 2200, and then I'll delete like 50, and then I'll delete like line by line until I get exactly where I need.
Okay.
So as long as you're in the general vicinity, it takes a little bit less time to just delete 2000 at a time rather than trying to find out where you are.
Any other questions? Yes, Yuchi, please. And please switch on the microphone so that we hear it.
So the state up is spin 1. Because your picture is not clearly where is the spin 1 and where is the spin 2.
Right here it says spin component 1 at the top, and then right below that will be
Can
spin
you use
component 2.
Can you use the pen to indicate? Use the pen to indicate which. Oh, okay. Here. Thank you.
Any other questions? Okay, let's thank Stephanie once again. And the next presentation is by Jon Vogel. So he will tell a story about possibility to convert the computation of VASP DFT results into UV visible absorption spectra. And then he will make a comment about effective mass of an electron, which is important for semiconductors. Okay, Jon, floor is yours. Okay, we are waiting. So by now we were doing very good with timing. So we should keep the same pace, having a limit less than 10 minutes presentation plus questions. And the talk that Jon is going to present is our first attempt to describe interaction of light with matter. So how the external light source can perturb the property of material or probe the properties of material. And the methodology that Jon is going to present will be the introductory approximate way to describe this interaction of light to matter. Okay, I think we are ready to go further.
Okay, so we're going to be taking a look at plotting absorption spectrum.
Excuse me, we're not seeing any slides from there, no visual. Everything's gone.
Oh, yeah, they're not. Student calls the screen capture. Yeah.
So we do have a little break before Jon actually starts, and you can spend this time just to stretch yourself or prepare questions to the next speaker and think ahead what you would like to know and what would you like to ask about finding and plotting absorption spectra.
Can you guys see it?
Yeah.
Can you go?
We can see it. Yeah.
Okay.
All right, so we're going to be taking a look at how to plot absorption spectra and also looking at energy and momentum relations and plotting those. So where we need to start is taking a look at the transition dipoles, which are allowed energy or electron promotions between different orbitals. And we're going to take a look at the ones that do not equal 0 or that have an energy difference that are about the same energy as the light coming in. So the transition dipole is given by this equation here, and it's related to the absorption spectra equation, which is this bottom one here, by the correlation between the oscillator strength.
Jon, can I stop you for a second? Would you please add the dr symbol to this first equation? Okay, yeah, thank you.
All right, and then this one should also be times some constant on the bottom. So these are just going to end up plugging in this way, and so this is how we're going to come up with the absorption. As Stephanie was just showing, you can go into your outcar file, and you end up making a states file, which will list just the orbitals and their energies. This list of orbitals is not actually for the model we used in class, so there should be 40, but this is for a different model. This is the same step that she showed, just making sure that the outcar and states files are ready to go. And so there are a few different files that we'll need when we make our oscillator strength file. And so what we need is we copy our states into an energy pop file, and we will also need the wavecar file, which is generated from VASP. And if you put in the command vi and then input overlap, what you can do is you're actually creating a brand new file. And by doing this, you go in using the insert command and you put in the first. This is the first state, and then this is your last state. And those are the two values that you'll put into that file, and you save it through the escape :wq exclamation point command, and you run this this OS dipole command on the bottom, and that will generate the OS strength file. Within the OS strength file is actually the discrete list of the orbitals and which transitions are allowed. So if we look at the I column, that is just one orbital number, and J is the second orbital number if we're looking for a transition from I to J. The oscillator strength is the third column, the energy difference is the fourth, and then the electron occupation, so the number of electrons in the orbitals are listed in the Fi and Fj columns for the orbitals respectively. And so once we have this file made and we go in and make sure that values are in it, we run the command of this spectrum IMP1, and so what that will do is it creates it creates a file called spectrum out of that, and through the next one we want the SPE files, and that's just through plotting using the new plot. And so what that gives us is the SPE.ps file, and then just like any other PS file, we can use the PS to PDF writing to make it into a usable file that we can download locally. And so that's what I did. And so this was a model we did in the lab, and the absorption spectra that came with it. So one of the things we looked at, we put in periodic boundary conditions when we built our models, and an important part is that we need to have our variation to our K points in the same direction that we have the extension in the periodic boundary condition. So in our case, we use the Z direction. As the K points were momentum descriptors, and we use those in the Z direction. And so taking another look at a new function that we learned this past week was dispersion, and looking at how particles can move within the materials. So what we're going to want to do is this top file, or this top little box here. This was the anyways.
You can type escape just once.
So that was the K points file, is this top one, and we edited in the Z direction. And we also changed this NSW value to 0. And that's going to take it so that it just looks at single shots instead of having NSW equal to 1. And so within this new directory that we created of dispersion, we need to copy over the 4 normal files we need to run VASP. And instead of just copying the postcar, what we want to do is we want to copy the contcar as the postcar into this file. So another thing is looking at VASP calculations that end up giving us many different K points, and that's very different from having just one K point. And so what we want to do is we want to take the number of K points and the values, energy values with those, and plot them together. So if we go, the commands here are going to what we're used, but if we go back to here, if we're grepping the K points, so we see this K point 1, and then this is actually the 6th column. And when you change the K points file, what you'll actually do is you'll have varying values within these K points for each different K point. And so these commands are how we're going to get the values out of the outcar for which we'll need. And in this case, this command was for my HOMO orbital, and this was for my LUMO. And so these numbers, 26 and 27, were corresponding to which orbitals were which. And so the next command here is combining the files, and what they give us this momentum, the valence band, and then the conduction band energies here. So now that we have this file created, what we can do is using this new plot, we can actually create it this way, and we can look at increasing in the energy direction for the green line, or for the electron, and then the whole energy decreasing for this bottom line. And so, then another thing that we were looking at is the effective mass, where the relation between the energy and the momentum. Whereas if you have one or a number of sets that have the same K point, or with varying energies, all that's left to vary is the mass of the particle. And for a better description, physics textbooks can derive it and explain it a little better than what I can right now. But kind of from what I gathered, it's the forces from the surrounding atoms or external fields that hinder or promote speeding through the material. So, and then these were the actual plots of the orbitals that I was running from a different one. Whereas this energy momentum plot, the lines are actually very minimal. They're very flat, and that has to do with the fact that these are these ions are very isolated, and so that the particles don't actually move from one to the other, and so that's why they look like this compared to these graphs where we had it in a period going in the z direction where they could move from one to another. So, yeah.
Okay, yeah, let's thank John once again. And questions, please.
Yeah, can you tell me a little bit about periodic boundary condition, like how we do and what is it for?
Okay. So what we do is, if we look with the boundary conditions that we did, we actually created this as in Mohammad. He gave kind of a unit cell that we used to reproduce, and so when we were looking from for these distances, we wanted to keep them separate enough so that they were not touching and forcing each other, but it was also that they were close enough where we could have certain interactions within the given direction that we described. And so, Mohammad, did you have any equations with the directionals? If you look in an email, did you Dr. Killen sent you there are certain equations given for what a periodic bounding conditions are. And so if not, otherwise I can send those to you.
Okay.
If you would like.
More questions to the speaker? Okay, if not, let's thank John once again. And the next presentation will be by Yuchi, and she will help us to bring from this abstract simulation of materials at 0K, at zero temperature, at optimal geometry, to real world where all ions, all molecules do experience thermal motion, and we need to go forward and model it explicitly. So Yuchi, please, floor is yours.
So first, I want to review the DFT. So this is the flow chart for the DFT. So when we get the input, the position of ion, the number of electron, then go through the theoretical process, then we can get the new total electron energy and the number of the electron and the new position. And then I want to review the geometry observation part. So first, we put in the input, the input. Then we through this process. Then we can get the new position, and the new geometry position, and the new energy. Then if you want to do the molecular dynamics, first we want to do the heat the system. This is the manual of the heat process. And here we copy the postcard. This postcard should be, we copy the countercard from the optimization geometry optimization and as the postcard. Then I will show the in-car of the heat. So here we notice that the N block is the number of the ionic steps between kinetic energy scaling, and these two is we set up the temperature you want to heat the system. So the temperature beginning is 300, and I set up the temperature end is also 300. In the beginning, the system, all the model system, the temperature is 0K. And why we need to heat this system? Because we want to provide an external energy source for the system, give them energy. And so give them like the kinetic energy. This is the formula for the kinetic energy. And this is the term is the momentum. It is depends on the velocity. And this formula show how can we to get the initial condition of the velocity. So it's based on this formula we can get the initial velocity. So the DRG, this one is stand for the initial velocity. And so look here. So when we give the heat is 300, but look here at the T equal 1 is 300, but T equal 2 is come to here is 0. That is because it's the convert to in the potential energy. So look here, so it's 1, 2, 3, 4. That means it's N block, so we set up 4. And we can compare the when we done the heat process, we can compare the first postcard and our countercard. They have the different. In the countercard, we have this. This is our velocity for the H ions. So then we can do the molecular dynamics. So when we need to copy the countercard from the heating, then to rename to the postcard, then we can to copy the in-car molecular dynamics, then run the VASP. Let's we see what's in the in-car molecular dynamics. We only to make sure this one. Make sure it have the 1000 steps. And this is the flowchart of the molecular dynamics. So we give the initial position and the velocity, then we compute the theoretic process, then we can get the new position and the new energy. So what is in the outcar for the MD? So it contains the energy of orbitals and the temperature at each step. So we have the 1000 steps. And we can plot the orbital energy when it's done. And but the time is limited. If you want, I can show you how to do the fluctuation. Is we can plot the Ks orbital energy as a function of the time. That's all.
Okay, let's thank Yuchi for nice presentation. Any questions from the audience?
Yeah, I have a question. In that temperature, we have two initial temperature and final temperature, right?
So you mean the heat process?
Yeah, heating process. Can we have a higher temperature at the beginning and lower temperature at the end so that we can see how it cools down?
Yes, we can. So for this experiment, we set up 300 and 300 end. So you can set up the 0 and or 300, but it's hard to get the final temperature is 300. So if we give the constant the temperature, it's easily to get the whole system can get the 300.
Can I add a comment? So for some practical reasons, for some simulations, you may want to simulate annealing, the preparation of amorphous materials.
Yeah.
Then you need to do several runs. You need to heat model, let it perform molecular dynamics, and then you can abruptly or slowly cool it using the same in-car. So instead of heating, you can run the cooling, putting the initial temperature higher and final temperature lower. And you can simulate how the cooling is going. Okay. This is possible. Other questions?
What you said, like NSW, what is that?
So what was the NSW?
100? Yeah. You said 1000 steps. What is that?
Yeah, this is, so for the heat is the 100. For the molecular dynamics, we make sure the NSW is 1000 steps. That is enough. We need to long step for the molecular dynamics.
Oh, it is the step that we give.
I have another question. Can you please show the slide with comparison between pros car and con car? Yes, this one. So you are highlighting the block with in red.
Yes.
Right after the word direct. So I think you wanted to say that everything that goes after the word direct corresponds to coordinates. But if you go below your highlighted block, then next block of data corresponds to velocities. So there are two sets of data, first for coordinates and second for velocities.
Yes, because it's too long, so I just cut the data. So the first direct means the coordinate of the ion. Then after the coordinate of the ions in the outcar, we have the new data. That's for the velocity.
Yes, very good. Very good. Let's thank Yuchi once again. And we have last presentation by Vinothini, Balasubramanian. Then I'm pronouncing it. And the presentation will be about the opportunity to post-process the results of molecular dynamics and visualize them in a form of movies. So I anticipate that after the presentation, Vinothini will show us some actual movies. Okay.
Can you hear me, STSU?
Yes, we can hear.
Here's my topic, making movie of the molecular dynamics, what we done with the VASP software. And hopefully everyone loves movies, so it's really a good opportunity for us to make some real movies. And here are few of the steps how to get the movie. First step is to use the command line, what I have showed here. And if you type that in your folder, then this command line will help you to get the movie in the format of .xyz. And in the second step, make a separate directory for the movie. You can name the folder of whatever your convenient name is. This is because it's going to make separate images in the frames, so there'll be like more than 50 or 100 frames, so it will not clumps up with your rest of the data files. So it's good to have a separate folder for this. Then in the third step, make sure your movie file is there. Just copy the movie.xyz into your folder, and if you check LSLT, then you will see the movie.xyz file in your folder, whatever you have created it. And then now, as we all know from the previous presentations, the .xyz can be imagined, like visualized in the software JMOL. And here, when you open up the .movie.xyz file, then you can see there is a tab called extras, and in that you can animate your .xyz. And here is the another dialog box which opens up, and if you click the play button, then you can visualize how the atoms are moving. Then so we have known that the movie XYZ, and now how to visualize it in the Molten movie. When you type the Molten movie.xyz, this is your .xyz file, and then there will be a dialog box opening, and here you can see the exact file, exact system, whatever we are looking for, and there will be a Molten control dialog box which will be opening up. And here we do have lot of operations you can just experience on your own. And here I will show the very important icons. Here is a camera button, and here is a movie button, which is very important for us to make the movie. So when you hit the camera button, it starts giving you the image of the system, whatever you are studying, in the frames format. And then if you click the movie, then it will start moving, and then it will start storing into your file. And then here is a command line which used to make in the movie format, so that it can be visualized in the softwares. And here is this command, this line is mandatory, and this one you can rename it on your own convenient. And I have copied the file into my own system, and it will be in the .mov format, and that can be viewed in any softwares like VLC or QuickTime Player. Or
can I ask a question on, as we go? So in this long line, can you please navigate to the center of the line and find the word that ends with .gif, and maybe circle it? Yes. So if we all are looking on this line, we should understand that previous slide that Vinothini was presenting is generating about 100 .gif files that do contain snapshots, one image, one geometry, one configuration after another, and they all are named. They name started with MOL, then there is a number of time step, and then .gif. So there is 100 GIF files with images, subsequent files. And the command that Vinothini is highlighting right now is a program, a code that combines several images into one movie file. So you can put there your own photos on the cluster, and then run this command and combine your photos into a real movie. or maybe use some other software. But what this command is doing, it is combining images into a video. Okay, sorry for interrupting.
Then now we have got the file in the .mov format so that we can upload it in the YouTube. So if you go to the YouTube site, you can see an icon called upload. So when you click on that, this box will open up. Then you can select your files to upload. Then whenever you are uploading it, you will see a lot of different descriptions. Here is the title, so you can rename it, edit it, and here is the description, so you can add description of what the model is, what the system is, and here is the tags which will help. We can just, like, if say for this particular system, that is TI408 nanowires, I have given nanowires TI408 molecular dynamics and also the University of South Dakota, so that this will helps to increase your views also. And here is the category box which says, like, you can choose like sports, gaming, and here I have chosen the science and technology. And then when the upload is done, you will get a link which is highlighted in here. Showing.
Seems like our audio is gone.
It's in the writing format. It's pen and ink.
Okay, I think we should respect time of each other and thank the speaker right now. So you can send your file as the link as an email attachment, so that we all try. Thank you all for making a great job of doing those presentations. It was really helpful, and I hope we came to the same level of practical skills. And now let's focus on our independent research project. And for the research project, we may plan to include the video files as a part of PowerPoint slides, so that we do not see this technical delays, because switching from one software to another one is typically may not work. And if you incorporate your movie file into PowerPoint, it will be working right away. Okay, thank you, and Meeting is dismissed.
Qué padre,